Welcome to the talk, ZigZag Automatically Hardening Web Applications Against Client-Side Validation Vulnerabilities. So this is work together with Robertson, Engin, Kirda, Kruegel, and Giovanni Vigna from Northeastern University and UCSB, respectively. Okay, so this is how web applications work nowadays. We have programs included from different sources which are running in different contexts in the same browser window. They are in different iframes and they are well, oh, I'm sorry. Is it better? Okay. So these are all running at the same.
Use the mic closer to you.
Does this work? Okay. So these these are all running in the same browser window at the same time. However, they are these can communicate back to the web service where they're coming from, so the original origin. However, so they are separated by the same origin policy. So a script cannot just communicate back to any server which is out on the internet. The same origin policy is enforced implicitly by the browser. So these authors or websites don't have to keep this in mind. This is automatically done. However, for these mashups nowadays, so to communicate with between scripts in the browser, we can use postMessage to send messages between scripts without going for a round trip back to the server. So this is useful if scripts want to talk to each other. However, the same origin policy does not apply here. I mean, it is explicitly bypassed. And what this means is that the developers have to take care of authentication here themselves. So these developers have to take care of these things on their own. So the issue is if this is not done correctly, an attacker, for example, can send if an attacker can take over an iframe in one of those websites, they might be able to send a message with exploit code to another frame and, for example, steal a cookie from there or act on their behalf. So these are client-side validation vulnerabilities. So these are bugs in the client-side portion of web applications. And so this happens if untrusted data, so this can be from another frame, is used in an unsafe way. So the validation of this data is either completely missing or it is done in a broken way, which is not lining up with what was intended by the developer. Okay, so attacks that can happen here. So if a developer expects an origin of a message to be only a particular site, but actually this can be bypassed. Or another script is able to inject commands on behalf of a victim script and act back to the server where the script is coming from, or is able to steal a cookie or write a cookie of a victim user. So how do we defend against these, or how do we detect these? Looking from the server side, this all looks like actions of this victim user. So there's no insight into what's going on in the browser, really. So we have to move all these defense and detection techniques in the browser to be aware of what's happening. So what do these look like? This is an example from a site that is still vulnerable. So we reported this bug. It was fixed, but then did some regression. So we just renamed this to domain.a.ru. And here we have a listener function which is receiving an event. So whenever a post message is received, this is executed. The event has a property origin, which is set by the browser. So here we have the origin set as the origin of this site. And here they check with index.auth whether the string is contained. And if this is successful, they evaluate the data property of this object. So this is a string which can be sent by this other frame. And the code below is attaching this to the message event. Okay, so the issue, of course, is that they have to not only verify the origin in some way, but they have to do it correctly. So what they do here is just they check for substring. And so this is a pretty popular mistake with these. So a counterexample, for example, is domain.a.ru.attacker.com or any other string, really, which is containing this string. Okay, so how would this attack work? The attacker is sending an email to this victim user with a link of its website, or is otherwise getting the user to click on something. So here we use website.com or anything else that can look unsuspicious. In here we have two iframes. One is domain.a.ru and the other one is domain a.ru.attacker.com. What happens here is then we can send a post message from this attacker side to the benign side, which is going to execute this code, and we can leak back a cookie to the attacker. Okay, so the goal of our project was we wanted to harden JavaScript programs which were benign but buggy. So these are programs which are not written with malicious intent, but the developers are trying to make a good application, to put an honest effort into doing it, but there's still going to be bugs which they're going to overlook. For this, we want to be fully automatic, so we didn't want to generate suggestions on how to modify these programs. We wanted to do this end to end, and we wanted to have all the detection and defense techniques in the browser alone. So we didn't want to either we didn't want to change the browser, or we didn't want to write the extension. We want to do this all in JavaScript, and probably most importantly, we want to handle unknown vulnerabilities. So we didn't want to act on list of signatures which we check in the browser. We want to deal with these unknowns. So we are not the first ones to work on client-side validation vulnerabilities. So this has been shown to be an issue before. So 84 of the top 10,000 sites are vulnerable to this. And there's also already 2 bug finding systems. So Flux and Kudzu are tools which can find exploits for existing programs. And there's also defense systems, but they require either changes to the site or changes to the standards. Okay, so overview of our system. This is an anomaly detection system that is preventing client-side validation vulnerabilities in the browser. We're doing this by instrumenting the JavaScript code. So we are rewriting these programs. And so this acts in 2 stages. So first, we are learning a model of benign behavior while the user is executing these sites. And then later, we can generate this model of benign behavior and prevent attacks in the browser. Okay, so what does this look like? So ZigZag is our system boundary. We have this proxy set up in the middle. The browser is requesting a website. So here comes the JavaScript program. It ends up in the proxy. Here we instrument it. A tool which we extended from this is the Clojure compiler. So we are inserting this trace data, which is a trace collection program, which is helping us collect data. While the program is executing in the browser, the client is sending back traces to the proxy where it's being stored in a database. So we are collecting these execution traces. We are doing this with multiple users. We're doing this multiple times. And once we have enough traces, we can run our invariant detection tool. And this output of this, we have a list of invariants for these programs. Okay, what are program invariants? So these are assertions over program points. Assertions over variables at program points, like x equals y or x plus 5 equals y and such. And these are detected dynamically. So while we execute, we are collecting these variable states, and later we combine this into we run statistical analysis, and we have as output those invariants which are likely to hold in the future. So a tool which we extended for this is the DICON dynamic detection system. Okay, so invariants which we support standard invariants by DICON, but we added our own ones to make this more fitting for this CSV problem. So, for example, we extended the string detection by check for whether a string is actually a JSON string, whether it's an email address or URL or, in fact, a number. We also have relearning typing. So JavaScript is dynamically typed, so so developers don't specify a type in the program, but usually a variable will be used only one way or another, so we can learn this too. And we're also doing some control flow checking based on the invoking function of a function. Okay, so coming back to this running example we had, if we run our tool on this domain a.ru website, we would see that the listener function is only invoked from the global scope. So no other function is invoking this function directly. It is only catching events. And the type of argument 0 here is object. And the origin property of this object is http domain a.ru. And the data field is one of 2 jQuery commands. And so we checked this by manually analyzing the code of the site, and so these invariants turned out to be correct. Okay, so after having these invariants generated, we can switch to the enforcement phase of this tool. Again, we have the user request a website. We're sending the JavaScript program to the user. When it's in the proxy, we are again running our tool, and now it is inserting the invariants into the instrumented code, so we can enforce them at runtime. So we send this to the browser where it's being instrumented. Where it's being executed, and so to the user it looks like a regular execution of this website. So we have this attacker trying to exploit the user, but it would violate one of the invariants, and we would either alert the user or terminate the execution of the program. So in more detail, if we, what does it look like if we instrument? If we have a function which is invoked with A and B and returns the sum of it, we would insert a call to these trace functions at the beginning and before the return of the function. So the call and exit are based on learning or enforcement, either collecting trace data or enforcing. We have all these, so these IDs in here are to identify the program point and invocation. And the last argument to exit trace is the return value of this function, which we return if this is successful. So if you look into this function, we have a switch between all the function IDs. So coming back to the running example, if we have function, this is function 0, we would check where the type of v0 is in fact object and where the origin property is what we learned before. Next, we check whether the data property is either one of those 2 values. So if this were to be exploited, it would fail at the first assertion. Okay, so ways to deploy ZigZag. We came with 3 ways to use this. The first one is this transparent proxy, which we described before. So we can deploy this at a gateway, and while the users are browsing over this, we are rewriting the code with ZigZag. And however, there's some latency involved, so we have to check the code while it arrives and rewrite it. But more on this later. Alternatively, we can do on-site rewriting. So we rewrite we download the code, we rewrite it, and then we upload it again to a web server and execute it there. So the upside of this is we only have one-time instrumentation, so there's no latency with this, and it also protects all users. They don't have to go through a border gateway. However, here some collaboration with the owner of this website might be required, or invariant sharing. So we combine this transparent proxy approach with smaller networks, and they can later combine offline the generated invariants. So at this point in the project, we had 2 major challenges. So we had a working prototype, but first we noticed that when we went to real-world websites, the execution in the browser was really slow. So we had a big performance hit with this, and the sites were hard to use. And the second issue is we noticed that a lot of websites are generating JavaScript on the fly. So they're including user data in the programs, which ends up that these programs were not equal. So if we go to youtube.com, for example, we will have new JavaScript programs every time we go there. So this was an issue for anomaly detection. To solve the first one, we were just asking ourselves which functions are actually relevant for our system. So it turns out that not all of them are security relevant. And so what we did is this lightweight static analysis run before instrumentation. So we checked the program whether a function is accessing any endangering, any interesting properties like the document or the window object, or has access to a XML HTTP request, eval, and such. So if they do, we label them as interesting, and if they don't, consider them safe and don't instrument them. And as output, we had a faster program with same security properties. Okay, and these server-side JavaScript templates. So what we noticed is so the sites are generating this JavaScript code either with configuration based on the user properties, or the username can be included, timestamps, password, salt, things like this. And so many of these top 50 sites are using these techniques. And so the issue, of course, is for us, we couldn't easily tell whether two programs are the same. Also, the ASTs were not always the same, they were only similar. And so the underlying problem was that we were not able to use anomaly detection here, because we only have a singleton training set. So we go to the site, we train, we go to the site again, we train from zero. So there was no reuse of invariants possible. So the question was how to generate these invariants over classes of programs. So programs which are all generated by one template on the server. So what this would look like if we have a larger program on the server side is being generated there, and we have this state variable with user and session property, and there it's being templated and filled in with the actual username and actual session ID. We could have multiple, so we can have 3 different instances of this on the client delivered. And so the first idea was to look at the AST and just compare this. But turns out that many of the sites were also serializing out of order, so there was no way to rely on the AST always being the same. Okay, so what we came up with is this. So the question was, when is code really similar, or when is it different? So when does it belong to the same class? We said if values of primitives differ, so if a string is different, or a number is different, or object properties differ, this is okay. And if there's differences in the AST due to either missing object properties or they're just out of order, then we can still consider this as member of the same class. And so the 2 things we wanted is that we wanted to be able to tell quickly whether a program belongs to the same class, whether 2 programs belong to the same class, and we want to be able to instrument these programs quickly. So as to comparison, we once we suspect a program to be a member of some class, we get the AST from this uninstrumented program, and we look for these program points for generalization. Once we find these, we replace them with placeholders. So we store a map of these points in the program, which we use for further instrumentation. But so all these templated values are removed here, and all of this reduced program we use. So we run our script to generate a string representation, which is going to be always the same for programs of this class. So this helps us to match. Okay, and so how we do this, we remove all primitive values. So we reset strings to empty string. We're removing object properties out of objects, and whatever remains in an object, like objects in objects or functions, we order. And once this is done, we are instrumenting the program with our tool. And then if we receive a new instance of this class of programs, what we do is we look up the corresponding places in the program that match these placeholders, and we generate a patch set. So we know which point in the previously instrumented program we need to replace with these new values. And so what we do here, so the output of this is, of course, that this is faster to instrument, but most importantly, that the reporting anomaly detection here to from equal programs to ones which are in the same class. Okay, so as for evaluation, we tested our system on 4 real-world bugs, which were representing different classes of attacks, and also we created a synthetic webmail application. So we trained our system on these sites, switched to enforcement mode, tried to attack, and we were able to catch these attacks, while the functionality was still retained, so the sites were usable as before. terms of performance, we evaluated the Alexa top 20. So these sites didn't have any bugs we were aware of, so we were just testing how fast these load during enforcement phase. And it's really median overhead of 2 seconds, which is 112%. We had no false positives with enforcement, so the sites were functionally the same. We also ran a micro benchmark where we had 2 iframes communicating with each other, and so you had an overhead of 0.66 milliseconds. So in this diagram, what we see is the comparison between the original load time of a site to the instrumented load time of this website. And this is the window load event. So this is triggered once the website completely finishes loading. So websites become usable before this. So this is an upper bound of when a site is finished loading. Also one outlier here is CNA COM-CN. So we had this site does take a long time to instrument with us. But we want to point out that this is a research prototype. We see there's ways to improve this further. Okay, so the contributions of our paper is we create this in-browser anomaly detection system that can prevent unknown CSV attacks in the browser, and we came with invariant patching, so we're extending this detection of invariants for programs to classes of programs which are generated by server-side templates. And to wrap up, client-side validation vulnerabilities can be prevented through invariant learning, and we were able to overcome these 2 real-world obstacles, so both server-side templates and this function whitelisting to increase performance. And so ZigZag is an effective defense against CSV, and we're able to enforce in the browser only, and this system is operating with a moderate performance overhead. Okay, thank you for your attention.
So I know you mentioned that on the sites that you tested, you didn't find any impacted functionality, but I'm curious what happens when there is a failure mode. You said that if one of your invariants is violated, either there's an alert to the user or execution is terminated. I'm just curious what that looks like and what happens if a user is using a site and it breaks.
You mean during an attack, or?
During an attack, or is it maybe, I don't know, is it possible that you might flag things that are not attacks?
So we didn't have false positives with this top 20, but so what happens if we detect something as an attack is we surf away to a different site, or we just alert the user at this point.
Other questions?
Adam Lerner, University of Washington. I'm wondering who you think is the right entity to be training and deploying these kinds of defenses. Is it the makers of the websites themselves, or should should browsers be doing this to every website that a user loads? How do you think that? Where do you think that responsibility and ability to deploy this falls best?
I mean, what would be best if the developers of the application do this during development, when you can make sure it's a benign training set, and then maybe integrate these assertions into the live program. So this on-site rewriting, I think this would be optimal.
Do you think developers who leave vulnerabilities like this in their code are more likely to fix them using this? Am I being a pessimist? I'm sorry.
No, well. Sorry. Can you repeat? Where it's likely to?
I was just wondering whether a developer who leaves these vulnerabilities. I guess my question is: does this make it easier for the developer effectively? Is that what you're arguing?
I think it might be good to include this into bigger applications which are maybe not maintained that well. So after maybe developers leave, this can be still included. If a developer is creating a site from scratch, might be easier maybe just for code review, but if a program is more complex, then this might be easier.
Sure. Thank you.
Thank you.
Okay, well, if there are no more questions, then let's thank all of our speakers again.